All right, number 5, on a day when there's no wind, you are moving toward a stationary source of sound waves. Compared to what you would hear if you were not moving, the sound that you hear has...
So this one says you're getting closer. You are running toward that source. So your frequency is going to be higher because you're getting closer. So the listening frequency is larger than the source frequency.
When we have a stationary source, what happens? Well, as those sound waves go out, you'll notice that the wavelength, the distance between these rings, stays the same, no matter in which direction you're going. So this wavelength we will measure will be the same as we move through it. We will hear a different frequency because we are moving. Correct, a higher frequency and a same wavelength. On a day when there is no wind, you are at rest and the source of the sound waves is moving toward you compared to what you would hear if the source was not moving. The sound waves you hear...
All right, so in this case, the source is moving toward you, but the key idea here, you're still getting closer. Whenever the source and the listener are getting closer together, a larger frequency is observed than is emitted. So a larger listening frequency than a source frequency.
All right, so we have the source, and the source is moving toward the listener. All right, so when that source is moving toward the listener, you do see a change in the wavelength of those sound waves, because as the source is moving, it's catching up, or it's not losing as much ground, I should say, with those sound waves in front of it. So we do see that the distance between the waves over here is different than the distance between waves over here. So when you have a moving source, you get a smaller wavelength in front, a larger in back. And since it's getting closer, we're on the front side, we will see a shorter wavelength. Correct, higher frequency, but a shorter wavelength this time, yes. 7, a sound source approaches at a constant speed and then moves past a stationary observer. As the source passes, the observer will hear...
So we have a frequency changing because the source is moving toward us and then moving away from us. So when it's getting closer, we have a higher frequency. When it's moving further away, we have a lower frequency, and just as it passes you, it drops. The closer it gets to you, the sharper that drop. If it passes near you, it's going to be a little more leveled out there.
Yes, a sudden drop in the pitch. Number 8, a sound source approaches at a constant speed and then moves it past a stationary observer. The observer will hear...
All right, so now it's the same question as the last one, except for we're looking at the intensity, not the frequency. And so as something gets closer to you, as R goes down, I goes up. And this is a squared relationship, so we see a pretty sharp increase. Now, the idea here is that a source can never actually get to an R of 0. So we never actually get to this axis. What this graph actually does is it goes off to infinity here, but because we can never get to those close distances, because two things can never actually occupy the same space, we never actually reach that asymptote. So there's actually kind of a break in the graph there, and then it comes back down. So we get this increase in frequency and then this decrease in frequency as it passes us.
A rise in intensity, then a drop in intensity. Yes, the intensity increases, then decreases. Good.